lectures to actual systems. We have 7 speakers, which means that we have 12 minutes per speaker. I'm going to try to enforce that because this is important, so everybody can tell us about the interesting projects that they have had. For the distance students, we're going to provide the file, to print out the files and provide all the slides from this discussion a bit later, but we're going to provide that so you can follow this topic too. Okay, without much further ado, the first speaker today will be, actually it's a couple of speakers, Christian and Neil. So tell us about particle trapping and manipulation.
Oh, yeah, you keep that one? Okay.
Yeah.
Can you hear me?
Yes.
No, okay, good. All right, my name's Chris, this is Neil, and what we want to talk to you a little bit about today is particle trapping using electrophoresis, using electric fields. And first I want to talk to you a little bit, why is this, interesting things, why is this useful? So we're going to go after that about some of the theory about electrophoresis, dielectrophoresis, and then go a little bit into the forces that are involved in doing these experiments, and then go into specific examples of non-conductive trapping, and then relate some of the results there to you, and then go specifically into the application we're particularly interested in our research, which is the trapping of conductive particles, and then go into practical issues and maybe even present some of our own material, own results here. Oh, thanks.
You're welcome.
Good thing you're doing that. Why is particle trapping useful? The good part that it's really one of the very few techniques that allows you to hold very few or even just one particle in a particular place, that allows you to examine just one piece or one colloidal particle. So obviously you can selectively isolate, for example, a cell and investigate the properties of that cell in biomedical research, or you can manipulate and investigate individual colloids, investigate their properties, and then do some nanoscale engineering using this trapping. And I'll come later on, I'll talk a little bit about examples, how we use that. Keep going. So the advantages of colloidal trapping using dielectrophoresis is that there are no moving parts involved. And it's just based on electric fields. So it's completely, you can actually make it contactless. If you use negative dielectrophoresis, which we'll talk about, then you don't touch the particle anyway, you just hold it there. And from an engineering perspective, the nice part is it's parallelizable. It's not parallel inherently, but you can make it parallel very easily. So this is a fabrication technique that you can scale. It's a simple bottom-up approach. You can have a wide, the electrophoretic force we talked about earlier is only limited to charged particles. This isn't. So you can use this in a very wide application range, which I've listed some of them, what the items that they have trapped, the particles that they have been trapped. I listed some of that down there. It's just an incredible range of materials. So going over some of the theory, we've seen this expression in class. This is dielectrophoretic force. It depends on the gradient of the electric field, obviously. It depends on the particle volume, and it depends on the so-called Clausius-Mazzati function, which for conductive particles, it's very easy. It's just always going to go to 1. So there's only one type of trapping you can do with dielectrophoresis with conductive particles, because this is just always a positive 1. But in non-conductive particles, this Clausius-Mazzati function is frequency dependent. So dependent on what frequency, on the frequency dependence of these dielectric constants, you can actually get positive or negative forces. And I'll let Neil talk a little bit about 2 different kinds, if you take that.
Okay, the 2 different types are negative DEP and positive DEP. We already saw this in class, but here's a good example of a simulation where they have the field strengths on the electric field on the right. And then you can see that in the minimum, in the center, you can see that the negative DEP trapped a particle in the middle, because that was...
Use the mouse though if you want to
Okay.
show. And press Control P. Press Control P. The mouse is going to right on the...
Okay.
Yeah.
You can see right here that with negative DEP, the minimum is in the center. The minimum gradient is in the center, and the maximum is along these edges. So you see when you have negative DEP, it traps it right in the minimum, and when you have positive DEP, it's along the edges. So clearly, it looks from this that this is better suited for trapping because it trapped the particle right in the middle of all those electrodes. And with positive, that the feedback, there's some sort of feedback or end pointing necessary, which we'll get back to.
Press that arrow. Yeah.
Okay, so here's the frequency dependence. You can see this is the same graph that we had in class. Over here on the right is an example. At 8 megahertz, we can see that the particles aligned in, this is during negative DEP, so the particles aligned in the minimum. But now when you decrease the frequency, it changes to positive DEP. So now they're aligned on the electrodes, and that's where the maximum gradient is. And then if you continue to lower it, now 70 kilohertz, there's osmotic effects that are this is still positive DEP, but you can see in the top one, the electrodes aren't aligned, so it's like a streaming effect from the electroosmosis. But on the bottom one, the positive DEP field gradient is still stronger, so it's still able to collect and trap in there. And then if you lower the frequency even more, the osmotic effect has more of an impact. But generally, in practical use, the best trapping is right around this crossover frequency. So we saw there's an example of where streaming potential can affect things. Let's look at some of the other problems. Brownian motion. If the particle, the particle wants to be trapped, but the Brownian motion, if it can overcome the energy barrier, then it can escape. There's also heating of the medium, which changes the consistency of the medium. There's electrohydrodynamic, which we just saw, and you can see here. This actually can help you because this is bringing the particles in and allows them to be trapped. There's particle-particle interactions, drag forces, sedimentation and diffusion when the solution's evaporating. The electrogeometries in the nanoscale can be, they cannot be what you think, and it could change the field intensity in the nanoscale. And the principal problem is observing these trapped particles. Really, as the particles get smaller, the main point here is the problems get worse. Because as the particles get smaller, the volume, the force, the DEP force, is dependent on the volume. So the force gets smaller, which means the Brownian motion can play more of an effect. So you have to use higher fields, which heats the medium even more, and all these effects. And then if you're, I'm out of breath. if your particles are on the nanoscale, then these geometries can really affect your these gradients, these differences in gradient can really affect you. And then clearly it gets even harder and harder to observe these trapped particles. So this is the approximate minimum particle radius for stable trapping. So this is the equation. So you would have to have this radius if you're going to be able to stably trap the particle. I'm not going to get too much into the details. There's a reference here if you'd like to see more of that. But let's continue into the electrogeometries because we discussed that could be a problem. There's the two-dimensional geometries. There's a dual lead, which is like a proximal probe, where that's this one right here, where a particle would hopefully be trapped in between these two electrodes. There's a quadruple or polynomial arrangement, which is similar to this, and it was what we saw on the first page. So this latex bead got trapped in between these electrodes, and this is good because you saw the field diagram, and there's a minimum at the center, and there's maximum around the edges. So this structure really is a good geometry for trapping particles. And there's the castellated structure, which you saw in the frequency-dependent examples that I showed. But there's also three-dimensional geometries, such as the octuple field cage, which is this one. And that's basically 4 quadruples stacked with something, a layer in between. And then there's microcage or chamber where they deposited rods on electrodes and trapped a particle. You can see that in here. Usually need 3 dimensions for stable end depth because the particle can escape along the z direction. Or you can just use a covered 2-dimensional design typically. And it's the enclosed area, not the geometry of the electrodes, that's critical. So you can have any electrode shape you want as long as the inside is the field is the same as a different geometry. So what's important is not the electrodes, but the field geometry inside. So now Chris is going to talk about the different applications for non-conductive and conductive trapping.
All right. Tag teaming back here. So obviously there's a lot of different applications for this, and one really nice one is you can test viruses, the infectivity of viruses, and And for example, you can check the cells that you can trap cells, and you can check for the malignancy. I don't know what it's pronounced. Malignancy of tumor cells, how bad these tumor cells are, because that is related to their electric capacity. Or then there was one example where we saw they coated AFM tips with nanodiamond by alternating using positive and negative dielectrophoresis. And there's all sorts of other nanoscale fabrication techniques that you can use. You could also use this to sort particles. You can, for example, because it depends on the dielectric constants, the relative dielectric constants of the two particles, you can use that effect to stream one way or stream the other way. And there's one example where we saw they had two different particles, and they sort of separated them out into two separate streams, very well defined. And then there's obviously you can do sensor applications where you build sensors out of these trapped materials. Yep. And then now the application that we're particularly interested in, that's our research area, is using conductive particle trapping, which you do with positive dielectrophoresis. The previous ones were mostly negative dielectrophoresis. Where what our research area is we are interested in the electric properties of molecules, so we want to have current voltage characteristics. So what we want to do is we want to have a molecule-coated electrode, or even coat the particle we want with a molecule of interest, and then have dielectrophoresis to come in and bridge these two electrodes, and then be able to measure them electrically, that path. And there are some people who've done that before. Hit the next one. And these are some results. There on the left you see an earlier study where this used palladium particles, and they were able to get trapping of sometimes single particles, sometimes they got a couple of particles to bridge. This actually didn't use molecules yet. On the right they had studies where this is actually a molecular coated electrode, and then they came and they trapped gold particles. And some of the interesting things is that as you increase the particle radius to the size of your actual gap, most of the time you get only one particle that traps in there, because once you trap, then you sort of you condense the field to that particular point where they bridge. Whereas if you have a very small particle compared to your gap size, you get these clusters, or we call them these grapes sort of shapes that you see on the bottom in E there. And depending on what size you use, and you get all sorts of different interesting effects. One hard part that you can sort of see from here is that you don't know when you should stop your trapping experiment, especially when you get like one of those grape clusters. You don't really know when you can't really measure how many there are while you're doing this.
But won't you measure the current through the electrodes and kind of decide when you see the current increasing or decreasing? Or
yes and no, but the hard part about measuring while you're doing this is that then you don't know the exact field you're applying. There was in that left study, actually what they did is they connected a resistor in series with this arrangement, and then they looked at the current that they got while they were trapping. And but the problem with that is that then you don't know electrically what you really are applying across that junction, unless you're very careful. And then there's this study actually that's been fairly recent, where they used this is kind of interesting. What they do is they trap gold particles also, and they get these gold clusters. And then what they do is they try to get these nanoscale break junctions, and then they electromigrate out a gap. And as you can see here, they apply, in C they show you the ramp that they apply, and all of a sudden the current stops once you break that junction. And you can see sort of in the bottom there how they melt actually the colloid due to the high current. And then you get this little junction there. Go ahead. So in practical terms, what we found and what other people have found is that you need high frequencies in order to do this thing, because otherwise you might get salts that from your solution that you get electrolysis on your actual electrodes, which is bad because then you create leakage current paths and it destroys your ability to measure this very low current that you get to a couple molecules. And then also as your solvent, we've seen this earlier, as you evaporate, you create sort of flow effects, you create streaming effects at the outside where the size essentially of the little drop that we put down on our electrodes decreases, and you drop colloids out of solution, you create all sorts of weird flow effects, and it affects your actual experiment. And then as we've seen, you have high current, which can sometimes melt. If you apply too high a field, you can actually melt a colloid, or you can melt a junction while you're doing this. And then also, since these are so small, you have to use SEM or some other technique like that to image those things, but then once you image them, you can deposit sometimes carbon films or other things like that, so that makes it really hard to measure after you image them. And it makes it also impossible to image them before you actually do the experiment, which makes your controls really difficult. And then obviously we said before that endpointing this is an issue, is difficult to do. Now I'll let Neil go over some of our results.
I think we skipped a slide.
I think so too. That's all right.
Let me see. Oh, here we go. That's strange. Okay. Here are the conditions we used. You could see, I keep pointing to it, the voltage peak to peak of the AC field, 5, 10s typically, and our frequency in the megahertz. We endpointed. We clearly didn't know how to endpoint at first, so we were endpointing by just a certain amount of time. And then we just used 8 microliters. It was important because here's our proximal probes and here's our structure. So you can see this right in here, and they'd be trapped inside. It's important to use the right experimental setup, because if you don't use the right setup, a lot of times people are not measuring with the oscilloscope across the junction because of a lot of transmission line effects. So it's very important to have the right setup, so you make sure you're applying and measuring the right field at your electrodes and then across your gap. Here's our one of our initial results. As you can see, these are 80 nanometer colloids. This was a great result. This is exactly what we wanted, because ideally you could put molecules on those colloids and actually measure the IV characteristics. We didn't do that. Not all of them looked like that, though. There's a lot of other ones that looked different. This one, for example, looks like we blew out the lead during our trapping, electromigration. Something happened. We're not sure, and I'll get to that later why. Over here you see the grape effect. Now you can imagine the electric field lines. And this is a great example of the electric field lines. And so the gradient, you can see how they're going right with the gradient of the electric field lines. And then over here you can see kind of like strange melting that might be occurring with too much current, and you can see a lot of those effects just in our own results that Chris talked about. And there's some other interesting issues. I don't know if you can see this, but we were pre-screening the electrodes under the SEM before we would run these experiments, but it was depositing a contamination film on it. So therefore, we weren't able to pre-screen these electrodes anymore because we couldn't get accurate IV characteristics if we contaminated the surface, and it also could change our trapping conditions and have an effect. Here's an interesting thing where off the probe we lifted the tip without turning off the signal by accident, and these colloids started to chain. These 80 nanometer colloids started to chain off of the tip. So that was pretty interesting, applicable to what we talked about in class. Here's another thing where the colloids were crashing out. Once the drop evaporated, you could see these lines of colloids. Here was our structure. This was covering the structure with the drop. And here's the SEM closer. It was denser. We were thinking about using the high density around at the crash out point for another application, but I don't know if it's going to work. And then these are our references. If there's any questions, we'll be happy to answer.
Okay. I have a comment about this drop, the edge of the drop. Brian Privo, who is not here right now.
Yeah, that's why we put down the slide.
Well, yeah, you have to show this and discuss this with him. He can tell you more about this convective assembly and so on. But he just missed this class, but he'll be around.
Yeah.
So it will be a good idea to discuss. But it's a very interesting research. Let's listen to the questions from the attendees.
Yeah, sure.
Fast does the actual entrapment occur?
Well, that's the difficult thing, and at least in our experiment, these are 80 nanometer colloids. We can't put it into an SEM, the whole system, and view it while it's going on, because first of all, there's fields that'll mess up the electron bombardment, so we can't see it. So you really have to try to endpoint it. Like Chris said, there's that one person that had a series resistor, and so when the gap closed, ideally it shorted that path, and a voltage came across the series resistor. But right now we're working on ways to endpoint it. We just ordered a new mask that we designed. It's very hard to endpoint these with positive DEP. You don't necessarily have to do it with negative DEP, but with our colloids, with our metallic colloids, we can only get positive DEP. So it's very difficult. That's a good question. It's very difficult to endpoint these.
From the literature, from what we've seen, from what we've seen in literature, what happens is it takes anywhere, like realistically, between a couple seconds and maybe a minute or two. Just ballpark.
Yeah, it will depend on the concentration of this
Yeah.
stuff.
A lot of things that go into that. Size of the colloid being a big one.
I missed this last part here with the colloid trapping. How are you using dielectrophoresis to
Okay.
what has the evaporation play in with the dielectrophoresis?
It doesn't play in. It actually evaporates too quickly.
Oh, this is a problem.
This was an interesting issue. I wouldn't call it a problem, but
Oh, okay.
yeah, it was just something that we noticed. And ideally, if we could get that density high enough, we could use it for another application within the Nanoscale project.
Yeah, that is true actually. Some people have been thinking about doing that, but I have not seen a publication. I can give you some website if you're interested about. But people have been thinking that you can assemble, let's say, conductive wires and so on in this method. Of course, I mean, like it's one thing is to make it work, and the other thing is to make it usable. But you can give it a try. It's an interesting area too.
Yeah, I actually talked to Brian after our last discussion about this exact same idea we have, where you just put a drop of super spreader on that, and it would hopefully instantly evaporate and leave the sort of film all over evenly.
Maybe, yeah, maybe.
Come to class, Brian.
Okay.
Well, that doesn't happen, does it? It sort of spreads it out towards the edges the most, right?
Okay, kind of, I mean, this comes to the issues now that it super spreads. The question is how you're going to dry it afterwards. Because unless you dry it, it then redistributes by evaporation. So, Brian, we're thinking about this problem with Brian, but it's not an easy one. So, I mean, let's leave it for now.
Yeah, it wasn't necessarily dielectrophoresis. We just thought it was nice application. Nice.
Yeah.
We talked about it in class. So
Sure.
Yeah. Did you have a question?
Yeah. For a like an application, say of sorting biological cells, like bacteria out of blood, for example, how would the high frequencies like affect like a cell in the solution? I mean, did you see anything about that?
I've read something on that. Well, I've read something on that, but it was really just like a short mention, like one paragraph essentially. It said, did a little hand wavy calculation and said, well, it's not that important, it's not that destructive, it's too low in intensity.
All right.
But yeah, it's just a hand wavy calculation.
But I'm not sure why you'd use higher frequencies, because I read something that said that that living cells responded to negative DEP almost at all frequencies. So I'm not necessarily sure that you'd have to use it, but it's definitely beyond. I'm kind of just thinking, I guess.
Yeah, you guys just showed that you had to use kind of like high frequencies for doing some of this stuff. So I was kind of curious about how that high frequency might.
Well, we had to use higher frequencies because the colloids are very small.
Mm-hmm.
These are 80 nanometer colloids, and therefore, I showed you the equation. You know, the force, the dielectrophoretic force is dependent upon the volume. So the smaller the colloid gets, the less that force is, and the higher fields you have to use, and the higher frequencies. And that was That was one of the problems with trapping.
All right.
What's the smallest particle size you can trap with this?
There's an equation for a minimum particle size. Although we've trapped 40 nanometer colloids, and I think you saw less than that, right, Chris? In the literature?
In the literature, they've trapped less than that, much less than that.
Yeah, I mean, it makes it very difficult to see. I mean,
yeah, I can immediately. This is in organic liquid or water?
This is in water with some stuff in it.
I can immediately see why this equation would be an under evaluation for water. Actually, you can tell me about that.
Is that not applicable to many mediums, though?
No, it will be applicable to any medium. But tell me, kind of on the basis of why this
So
equation
you're saying it should be bigger than this, or should be smaller?
should be smaller.
Smaller.
Why would why would some parameter in this equation be under evaluated if you just use data from literature in water? Suggestions? Kitten should know there, although he's silent, so he can't immediately. Now
Epsilon m that gets smaller with frequency.
it doesn't get smaller. Now in water, the polarizability, is it smaller or larger than the polarizability of the particle itself?
The polarizability would be larger, right?
Why?
Because it's water.
Um,
I don't know.
yeah, that's a bit too specific. What else do we have in water?
Sorry.
Right. So you have a counterionic atmosphere which has polarizability which can be very high actually. So in water, because of the additional polarizability from the counterionic polarizability, it can be much more polarized than if you just assume that it's the bulk of the particles once it gets polarized.
So epsilon m would be larger than expected, so therefore.
Right, and the size will be smaller.
So that means that the actual size includes the counterionic atmosphere, meaning the size of the particle could be smaller?
Not so much the actual size, perhaps, rather than the actual amount of
the effective polarized size?
of charges being separated. I mean, the additional charges, just because the counterionic atmosphere can move around the particle and separate a little bit from it.
So also that this particle, like this is only really considering Brownian effects. It's not
Yeah,
considering
yeah,
all of,
yeah.
like they said, the electrohydrodynamic forces are really, if they're bad, then they're really bad.
Uh-huh.
So you know.
Okay, anyway, very interesting presentation, guys, but we have to move on. I mean, like, it's really a little bit... Raj had a question, but you can ask afterwards.
Okay, sure.
Okay, who's next? Okay, Bin. I guess you exchange with Cellini. Okay, Bin. Now, Bin is going to tell us about the effects of electric field on polymer nanostructures.
कैसे भी चलेगा मेरे को जो ऑर्डर उसमें जाते हैं मैं जाऊँगा इसके बाद
Okay, I will talk about the orientation. Oh, sorry.
Yeah.
The orientation or ordering of Bloch copolymer nanostructure with external electric field. My name is Bing Wei. It's nice to introduce myself to you. Bloch copolymer is composed of at least two blocks. These two blocks are incompatible to each other, but they are connected to each other by a covalent bond. And Bloch copolymer can self-assemble into these amazing nanostructures because the features of these structures is comparable to the molecule to the size of the molecules. So these are at nanoscale. So these nanostructures are amazing and promising as a template to fabricate some nanostructure as you like. But there is some problems. The assembly of Bloch copolymer can only make a line structure in a small area, the size of tens of nanometers. But in application, probably we want much bigger size of these aligned areas. As we can see in this picture, in local areas it's aligned, but there are irregular structure between these ordered areas. So to improve this structure, we can use electric field. The possibility of using electric field to align this Bloch copolymer nanostructure is based on the difference of the electric permittivity between the two blocks. This is the electrostatic contribution to the total free energy. As we can see that the free energy depends on the local electric permittivity and the local electric field strength. So when the nano features like cylinders or laminae are parallel to the electric field direction, the free energy will be lowest. From this equation, we can see this point. So we can use the electric field to either change the direction of the nanostructures, or we can use the electric field to align this structure to make it ordered in much bigger area. This is an example of this experiment. As you can see, these cylinders. This is a picture of the cylinders aligned under electric field. The cylinders are perpendicular to the screen. So we can see that they are highly ordered in so big an area. As I mentioned, the self-assembly can only make ordered area in tens of nanometers, but in this picture we can see much bigger area. This is another example of the alignment of the laminae of block copolymer. Maybe you have noticed that the electric field intensity is much different between these two cases. What makes the difference? Okay, as I said, the difference between blocks makes it possible to align this nano structure with electric field. The difference between polystyrene and PMMA here, polystyrene and PMMA. Then the big difference between this FEMA block and the other two blocks makes it possible to align this nanostructure at much lower electric field intensity. So how can we use this nanostructure after you aligned? If you obtain this nanostructure that you like in block copolymer, then how can you use it in real manufacturing? As we can see, that this is an example. We can remove the areas of one of the blocks. For example, this in this picture, we can remove the PMMA block. Remove these light cylinders. Then many aligned, ordered nanopores are created on such a film. Then in these pores, if you can manage to deposit some materials you like, as in this case they deposit silicon oxide, and we can form this ordered array of silicon oxide. Furthermore, we can remove the matrix components, the polystyrene. So in this picture, we can see this highly ordered silicon oxide posts. They are aligned in this area. So my presentation is short. It comes to a conclusion that the block copolymer nanostructure are excellent template for nano fabrication. We can because of the size is on nanoscale, and it's
nano?
Excuse me.
How nano? I mean, how many?
Several nanometers or tens of nanometers.
Compared to the length of the rods being what?
Or you cannot compare to the. I don't know the comparison between the size of the particles or cylinders between and the length of the block, but they are close to the gyration diameter of the polymer molecules.
You can change it by changing the molecular weight of the blocks also.
Yeah,
So
the size of these features can be changed can be changed because of the size of the molecules. This is another amazing point of this method. And furthermore, this block copolymer can be mixed with homopolymer, so you can change the distance between these pores or cylinders. And the second conclusion is that this nanostructure of block copolymer can be aligned with external electric field. Okay, I will be happy to answer any question.
How do you dissolve it? You can dissolve it by solvent, right?
The
one of the block copolymers.
Okay, for PMMA, you can use ultraviolet ray to make it decompose, and then use acetic acid to dissolve the MMA.
Right, I see.
Basically, cross-link polystyrene when you have this ultraviolet light,
Mhm,
you can
right.
dissolve other component.
Okay, one
Yes.
more question and we can move on. David.
Do the structures become networked after you dissolve the material out, or do they maintain their separation from the others in the matrix?
When you use electric field to align this structure, this polymer has to be in the state of melting state.
I'm sorry?
Above the
Oh, melting.
melting temperature. So you can align it, you impose an electric field on this melt, and then cool the temperature down to lower than the glass transition temperature. So then the structure will be solidified there. It cannot move anymore.
Okay, we have to move. So I mean, like we have to move though. So okay, Raj.
Okay, I'm Rajendra, and today I'll be talking about fabrication of colloidal crystals by dielectrophoresis. Just to see how a colloidal crystal look like, it's basically a very nicely arranged crystalline balls, and you can have different structure of these balls arranged in different fashion. And I mean, whenever you go to a conference or something and you present something, first question that anyone will ask is, why do you want to do this? So, I mean, these colloidal crystals, they are useful as photonic crystals, and photonic crystal is something by which you can change the direction of light, and these are useful in various applications such as lasers or in antennas, solar cells, etc. Okay. So, since I'll be talking about how to prepare these crystals by dielectrophoresis, but prior to that, you must know how you can prepare them by other methods, so that you will understand the potential of this dielectrophoresis method. So, I mean, I'll just present two techniques. One in which you basically evaporate the solvent in which your colloidal crystals are present, and these particles, they just settle down, and by sedimentation you form these crystals at the bottom of the beaker. And in the second technique, what you do, you basically heat the solution of this colloidal particles, and at the same time you insert a substrate, and you evaporate the solvent, and because of the capillary forces that are formed during drying of the solution, these particles, they attach onto the substrate, and then you form the assembly. So as you can see, I mean, these processes, they have a number of disadvantages, such as this crystallization is very slow, and you form very small domains of crystals of the order of some couple of microns or tens of microns, and these are usually polycrystalline, and this actually kills your purpose. I mean, why you want to make them? So we want an alternative by which we can prepare these colloidal crystals fast and in a controlled fashion. So that's where the use of electric field comes into picture, and particularly I'll be talking about this dielectrophoresis. So which means you will apply this alternating field across your particles. Okay, so very little work has been done on this issue. How to arrange particles by dielectrophoresis, and I can find only 2 research groups that have done some work on that, and one of which is Dr. Velev's group.
Pity that you're not getting a grade for this. You're not getting a grade for this class.
Yeah, I know. See, I did not even know that not many people are working on that.
I know who is working on that, but yeah.
Yeah. Okay, so basically what you do, in dielectrophoresis.
Consider registering for grade. I'll give you high grades.
See, I'm auditing this course.
Huh?
I told him, Dr. Velev.
No, joking. Okay, go ahead. No. Good.
Okay, you cannot blame me for that. I'm just auditing the class.
That's a pity, right?
Okay, anyway, so in dielectrophoresis, what you need is non-uniform electric field, and for this you have these 2 electrodes, and this colloidal solution is trapped in this cell, and because of the geometry of these 2 electrodes, the field is very strong here and it's very weak here, and because of the gradient of the electric field, the particles actually move from high electric field density to the lower one, and the particles move into the gap, and thus they form the crystal over there. So what are the driving forces? Why do they form crystal over there? Okay. Before that, let's say, what happens? You must have seen this picture a number of times before. On left side you see the scattering phenomena when the field is off, and on the right side you see this phenomena when the field is applied, and you see this very nicely ordered 6-dot pattern, which shows that your crystal is first of all, it's you don't have polycrystalline structure, and as the authors reported, they get very huge crystals of the order of 25 millimeter square, and which is really nice. Compare it with the tens of micrometers that other researchers have reported, and this is completely reversible.
This is the size of the domain?
Size of the domain. This is the size of the domain. So you may have a multicrystalline structure, but then one of the domains is about 25 millimeter square. Okay, so this is, I myself have some questions regarding this.
Okay.
Okay, so what's the physics behind this thing? So this is where our lecture notes come quite handy. So, okay, there are two phenomena. First, why the particles move into the gap, and as we have all seen, that this is because of the dielectric force, and this dielectric force is actually depends on this Clausius-Moretti factor, which basically depends on the polarizability of media and polarizability of the particle. And as we heard from the first presentation, this polarizability of the particle, it includes the counter-ionic atmosphere, and which is very important. Okay, these particles, they are actually attracted towards the gap, which is the region of high electric field density, high electric field intensity, if the polarizability of the particle is much higher than that of the particle, and which is the case in our situation. So the particles move into the gap, and if it were the other way around, then the particles would have repelled from the gap. Okay, once they move into the gap, why they form this two-dimensional crystal? And so this is because of the particle chaining. Each particle, it's basically a polarizable particle. So when you throw this particle into an electric field, its dipoles, let's say you have two particles, so there when these two particles come close together, their dipoles will like to get aligned in such a way so that the total energy is minimized, and the most favorable orientation is the one in which the two dipoles, they are like 180 degree to each other, and this leads to the formation of chaining like this. And once the chains are formed, these chains can come together and then they can form two-dimensional crystal, and this is because of the proposed electrohydrodynamical flow. And so I mean, basically this hydrodynamic flow is because of the flow of this your solution material because of the application of electric field. And I have come across this electrohydrodynamic flow in when you apply DC field, and I'm not quite clear about how you get this flow in AC field. And so this is where I will stop, and I'll just throw in a couple of questions for discussion. First one is, and what brings this change together into these two-dimensional crystals? I mean, what exactly is electrohydrodynamic flow when you apply AC field? And the second one is, can you prepare three-dimensional crystals with the same technique? And this is a very new technique. Not many people have worked on it, and I think it's pretty interesting. So,
do you have more slides, or shall we discuss this?
That's it.
I can give you some kind of, like it's kind of a thought for, if you just go to the, okay, now just stop when it's white. Let me give you some thoughts for discussion here.
Mm-hmm.
Could you press Control P? Let me give you some, now you have a, you don't have a, okay, this one writes. You have a particle, then you have another particle, and you have a dipole, and you have another dipole. Now, we don't have that much time, so I'm going to put this as a kind of a homework to think about at home. We can discuss this next time, perhaps. Now, then you have another chain, and the particles are like that. Now, obviously, these two interact with each other, and these two interact with each other. Now, the question is, could these two chains interact with each other? And if they do, how they are going to interact?
Without any solution flow.
Without any solution flow.
Okay.
Kind of, like I don't think we have solution flow, kind of, as such. But now we don't have that much time, so I'll suggest that we move on rather than discuss this right now. Next time the lecture is actually short, so we can have some continuation of this discussion. I have to finish the scattering and so on. So let me put this as a kind of homework, and let's move on.
Okay, sure.
Okay, thanks, Ranch. You should register for a grade. Thanks. Okay, now Shalini is going to change the topic here a little bit. Now we have been speaking only about purely electrical fields. But we can have other types of fields, and Shalini is going to tell us about that now.
Yeah, and you'll have to bear with me because this is my first presentation ever, so.
No.
Okay. There have been many optical devices that are being used these days, like optical stretchers, optical tweezers, optical traps. And what these basically do is they trap the particle, and then we can actually move the particle around, rotate it, translate it, and set it in a nanostructure fashion or in a colloidal assembly in a way we want. Like, for example, in the figure shown here, these are 3 micrometer polystyrene particles that have been trapped and put in the geometry shown. And then what's done is the solvent that's surrounding the particles in which the particles are suspended, they are photopolymerized so as to lock the structures as they are, and the particles just lock themselves in the way shown here in the bottom 2 pictures. This is more clear. So what are the advantages of actually using optical devices? First of all, the first and most important point is that it's a non-contact process. We don't actually have to touch the cell or the particle or anything that we are dealing with. And apart from translation, we can provide a rotation of the particles, and we can actually control the rate of rotation to a very high precision. And I'll show you how that can be done. Okay, so how do the optical devices actually work? How do they actually trap and micromanipulate these micro-sized objects? Well, as we've talked about dielectrophoresis in the lectures, particles of higher like in this case it's similar. The particle of higher refractive index, when it's in a solvent and it has a higher refractive index in the solvent that it's dipped in, it moves towards the light of highest region of the highest light intensity. It's analogous to dielectrophoresis. For example, when we have dielectrics in a solvent and they have higher polarizability than the solvent, they move towards the field of highest intensity because they can actually polarize themselves to counter the external field that's been applied on them. So if the electric field that's applied on them is like positive to negative, they can actually align themselves, like metals can align themselves opposite to counter that thing, and they can actually align themselves opposite and they get attracted towards the field. So this is similar to that, and the analogy is pretty justified because lights are actually electromagnetic waves, and the dielectric, as we saw in the lectures before, the dielectric constant of materials are actually proportional to the refractive indices of the material. So it's kind of a similar kind of a concept. But the origin of the trapping force using optical devices comes from the fact that light carries photons, and the momentum, the angular momentum or the translation momentum of the photons can actually be imparted to the particles that we want to move, and according to the particles, however much they absorb, reflect, refract, or scatter light, they can be moved around in nanostructure assemblies or composite material assemblies. So this is another figure in which polystyrene particles have been trapped in water, and in the patterns shown. So the general scheme for particle rotation that's described by like objects get trapped within the interference pattern of an LG beam and a plane wave. So what is an LG beam actually? It's somewhat like it's like a wave. It's like a helical wave, not just one wave. It can be, the helix can be, like there can be more than one helix intertwined with each other. Like in this case, they have shown 3 helix intertwined with each other, and this is characterized by the azimuthal index L equal to 3 in this case. So waves actually move in a helical manner. So it's like if we have 3 ropes intertwined with each other and we take cross sections at different positions, we can actually see the ropes moving, right? So it's the same way in this case. The particles, if this beam is it's shown on a particle, the angular momentum of these beams is imparted to the particle, and you can actually trap the particle within the wave forms of this phase fronts of this wave, and you can actually rotate the beam around as according to the lambda and L, product of L and lambda of the beam. So lambda is the length at which the beam pattern actually repeats itself. So in this case, in the first figure, as we can see, this is 1, this is 2, this is 3. So after this pattern rotates and it repeats itself in a cyclic manner, so 2 comes here, 3 comes here, and 1 comes here. So this distance that the wave covers is lambda. But only after L into lambda distance can the wave actually repeat the same pattern in this case. So in this case, L is 3 and lambda is whatever the wave that we're using. So we can actually control the L into lambda product of the waves to manipulate the assemblies of the particles. So like in this case, it can be recorded, the micro manipulation of the cells can be recorded using a camera. So there's a laser beam that goes through the lens and hits the mirror, and it goes through a lot of processes, goes through a hologram, and then bounces off a mirror again. And then this is a rotating glass plate. So we can adjust the interferometer in the system to actually change the L into lambda product of the light to micro manipulate the cell, and there's a camera attached to this which can actually record the micro manipulations of the cell. So this is the general way it's done. There are 2 theories which are prevalent in this field. One is called the LG scheme, the Laguerre-Gaussian scheme, which is the same as the general scheme that I described. And there is another polarization scheme by which we can move particles. In this, the particles that have to be used should be birefringent. So by birefringent particles, we mean is that if we pass light through a birefringent particle, it actually divides itself into two two rays. So they are at 90 degrees with each other. So the relative velocity between these two rays actually makes the particle, it actually rotates the particle. So we can actually rotate the particle in a way we want according to the velocity of the light beam that we are shining on the particle. And we can make it rotate or translate. And this way we can fabricate a nanostructure assembly. And these are my references.
Okay. Cool. So again, like this is a bit dual in the sense that you can think of you know that about the physical dual nature of light. You can think of it as electromagnetic wave, or you can think of it as a flux of photons. Now, in a very similar manner, when you have entrapment of the particles, you can think of the particle being entrapped in the region of highest field intensity, or you can think of it as being exchanging momentum with the light photons and eventually being focused there. But it's a very useful technique and it works very fine.
But it has a disadvantage. The optical, like I didn't state the disadvantage. The optical, the optical rays can actually photodamage the cell if you're dealing with live cells.
Maybe. Yeah.
So that's one disadvantage I could think of.
Any questions? Yeah, Raj.
Not particularly with this presentation. I mean, any kind of trapping. I mean, optical trapping or electrical trapping. I mean, whatever you trap, how do you remove it? I mean, once you switch off the light source or electrical source, your trapped material doesn't stay there, right?
Well, it diffuses, yes, right?
Yeah, so, I mean, if you want to separate your viruses or some cells, so you'll have to do it in situ, I mean, while your field is turned on, right? But that then you will disturb the gradient.
But, I mean, like it depends on what you want to use such traps for. Now, dielectrophoresis is why people are so interested in dielectrophoresis for viruses. Now, I mean, you have to characterize, for example, you have flux of water kind of coming out of your out of your sink, for example. Now, you want to know how many viruses you have inside this water because it may be contagious. Now, how many viruses you need to catch a disease? Kind of just a few typically, like 10, 100 or something like that. Now, this means that you can have a bucket of water with 200 viruses inside, and then you can catch disease out of that water, right? Now the question is, how do you find these viruses in a bucket of water? You can understand the problem, right? So the thing then could be to make the water flow through a device which is going to trap all viruses. So at the end, when the whole bucket of water flows through, I mean, you can count how many viruses were there in that bucket. So, I mean, like it depends on the application. I mean, you can have an application where you just want them trapped and you want to count them and check out whether you have this virus or another virus.
Or I can think of another advantage, like if you're dealing with antibodies, if you want to pick a certain antibody that you want to stick onto your glass surface, for example, immobilize it for immunoassays or something, you can actually, like deal with single antibodies. You can trap the antibody, fix it with the aldehyde, like functionalized glassite, which has aldehyde ends on the glass surface, and you can actually stick it there. And after you remove it, it just stays there.
Okay.
So
now, Vadim and Forrest, let's ask a question. Vadim and Forrest would like to tell us about some very cool application of electrophoresis. Now, we have been discussing kind of all those micro devices and so on. But you don't use micro devices at home usually. Although there are now these days there are micro devices in your car. What are the micro devices in your car? Electrical engineers should know. What do you have? What is the micro electromechanical device in your car? Yeah, right, yeah. But I mean, like you can think about some colloidal application where you don't have microscopic things and you still can use these properties for something that's of big practical importance. So let's hear about this then.
Okay, I'm Vadim Ferrov, Chemical Engineering Department, and I'm gonna talk about what's actually inside of tunable windows of expensive cars, and actually many other things too these days. There are two technologies used to manufacture what's called smart glass, and one is called SPD, suspended particle devices, and the other called is ECD, electrochromic devices. my presentation, I'm gonna focus on SPD devices. SPD technology allows to control amount of light passing through the glass manually, automatically. There is actually technology that allows to do it automatically when photocell is installed on the side of the glass. So how does it work? Basically, when you apply, there are rod-like particles suspended in a solution. When voltage is applied, it allows the light go through, and when you turn off the light, it goes dark. So this is actually a really cool application, but I want to focus first on how does it work physically. So you have those rod-shaped particles suspended in a solution, and when DC voltage is applied, for example, atoms polarize within the particle, and that creates a torque that will rotate the particle and make it align vertically with the field. It will all the particles in a suspension will align vertically, and this is the clear state of the glass. And the net effect of this is that the particle as a whole becomes induced dipole. However, in DC field, those particles will migrate to whichever conducting layer is closer, depending on a sign, whether it's positive or negative, and what's called clustering effect is gonna happen. And mechanically, what we'll see is that it was dark. We apply DC voltage, it stays dark. Nothing happens because particles will accumulate on the top and bottom and cover the whole surface. So to avoid that, of course, AC voltage is used, or also there is another technique that deals with encapsulating particles inside very small immobile droplet called SPD film. And I'm going to talk about that on the next slide, but I just wanted to mention some physics here. When AC field is applied, the field is reversed, and basically inertia and momentum on atomic level are negligible here, and particle, when field is switched, and when it's switched back, particle stays aligned the same way. Let's see. And there are some things I wanted to mention about the assembly here. Obviously, this is the liquid suspension, or the film within which droplets of liquid suspensions are distributed. Microscopic particles are suspended within that liquid, and then that suspension is introduced within two pieces of glass with transparent conducting material on it. And what's interesting, that transmittance can be varied by degree of voltage applied. So it's not only dark and clear state. Some facts about smart glass. It has no memory effects, so it doesn't matter how long it was on or off. It responds immediately in fractions of seconds. It has only one. It requires only one active layer of dielectric suspension that's located between conducting layers of glass. It's relatively inexpensive. It's about $1 to $4 per square feet right now on the market, and it's very energy efficient. It's been estimated that for homes it saves about 40% of electricity, and for big corporation it can reduce it up to 85%. it has a huge lifetime. It has more than 100 million cycles. It can be scaled and in very big proportions, and can be applied for example, sunroofs of the big buildings or something like that, because the voltage drop is very small across the conducting surface, and operating temperature is very wide. And finally, the transmittance, like I already mentioned, it varies from 80% in clear state to 10% in dark state. So even when it's turned on, it's clear, but not exactly. It scatters the light, and it actually only 80% of the light goes through. And I guess the drawback is not completely dark when it's turned off, so you can actually see through it. Okay, the applications. The picture on the right actually is taken from website of the company, the leading company right now in production of smart glass. That's called Research Frontiers. They hold over 350 patents, only US patents. I'm not sure how many foreign patents they have. And this is one of their smart glass door, office door applications. It's just being being turned on and off. And variety of applications obviously can be used for windows in office and home environment, vehicles. And what's interesting, they claim that they even planning to work with NASA to supply windows for spacecrafts, aircraft, marine. And I found that interesting that they're planning to use it for appliances such as microwaves, ovens, because customers say that they want to save basically energy, because they don't have to open the door. But in darkened state, it looks more aesthetic, I guess.
Has anyone of you guys read in detail The Hitchhiker's Guide to the Galaxy?
Oh yeah.
So they have these eyeglasses which become dark when there is a danger, so you don't see it and you don't get disturbed.
Yeah, that was what I was gonna say. That I wear sunglasses.
So like the ostrich sticking
helmets,
its head in the ground.
And they're planning to use it even for visors for spacesuits, and of course displays, PDA, pagers, cell phones, computer monitors, etc. Here's another picture. It's a Hanka Glass. It's one of the major glass makers in Asia. They, in collaboration with Research Frontiers, they produce car windows and car sunroofs, and that's an example of it.
So where's the power source? How is it?
You don't really see it. It's behind.
He holds. There will be wires to his.
Through the
sleeve. So
you'll see the power source in next. It's actually, this is a movie. It's inside this movie taken inside of the car with tunable windows and a sunroof. So you can see how it works. She just turns the knob and it goes dark. You can also see that it doesn't switch just on and off. It has some intermediate stages too. And you see the wire on the bottom. See over there.
Oh.
And here the sunroof and the side window are working simultaneously. Okay.
Okay, so just one question, because we want to hear also Forrest tell us about the competitive technology, which is the electrochromic glasses.
Yes.
Questions? Let's hear about the competitive technologies. Then I guess these two companies, I don't know whether they are at each other or they collaborate. But again, you can use field-induced orientation in molecular materials actually to make another type of windows and displays which are tunable.
All right. A lot of my presentation will be kind of a repeat of what Adam said. I investigated electrochromic windows and displays, and like Dr. Velev said, it's an application of electrophoresis. The basic thing about the windows and displays, you apply the voltage, they become darker. You remove reverse the voltage, and they go back to their initial transparent state. And you also have ability to change the degree of transparency with the amount of voltage. So this is the same as the SBD. Here are some applications. The one on your left is Gentex, making an auto-dimming mirror with this technology. And then also Sage Glass makes windows, and this is an example of a skylight. I'm trying to hurry up here. Here's another picture of this type of devices. The bottom is a simple display. You can use your imagination that you could use it for larger displays. So the question is, how do electrochromic devices work? This is the basic setup. It's a series of layers, and the most important are the 3 middle layers. When you apply the low voltage, you have ion transport from a storage layer through an electrolyte layer and then into an electrochromic layer. The ions typically used are hydrogen and lithium ions. And like I said, when you reverse the voltage, they go from the electrochromic layer back into the ion storage layer. And all the magic happens in the electrochromic layer. I investigated 2 different types, an inorganic and an organic type. Inorganic, usually like a transition metal oxide, is what's composed of the electrochromic layer. They're typically tungsten or nickel oxide. And the different particular oxide is what gives you the specific color. In the case we saw, the vibrant blue color is the tungsten oxide. One of the drawbacks of using the transition metal oxides as your electrochromic layer is that it has a slow response time. I read that it could be up to 1 minute from its initial transparent state to its darkest point. On the other hand, we have an organic electrochromic layer, which I read was one of these was a redox electroactive polymer. And this specific polymer is adhered onto substrate, and it's colorless in its oxidized state, and then it has color in its reduced state, so it acts as a chromophore in its color state. And again, it's triggered by the ions going into the electrochromic layer. And the good thing about these polymer electrochromic layers is they have a sub-second response time, so it's a lot faster than the transition metal oxides. And they're also less expensive than the transition metal electrochromic layers. And so I guess the difference is I believe the transition metal oxides give a more brilliant shade. Okay, and finally, this was a quick presentation. Future goals and concerns about this technology. It's not a self-illuminating, display or window, so you have to provide a light source. In the future, if you want to make displays applicable to current technology, we're probably going to want multi-chromatic displays. All of the examples you've seen are just monochromatic, so that poses a challenge to get multi-colors in your displays, and also faster display changes. And then I read one place was wanting to make what they called electronic paper, which was ultra-thin displays that are flexible.
Yeah, this last one is a very cool one, and I'll probably speak about this when we have the lecture on photonic materials. So you just know a little bit more about the electronic paper.
Okay, that's it.
Yeah.
I have a question in general. How robust are these? I mean, if you get a scratch on your windshield from a rock, does that change the AC field tremendously so there's going to be a huge... I don't know.
That's a good question.
That's a good question. I'm not sure.
I think they would probably has a protective layer of plastic around it, which is like your normal glass window.
Right.
So it does not...
But normal glass windows get scratched.
Right, but it's not
But it's on the other side. It's like a double layer coating, and the fluid is inside. So the coating is on the other side. It's not on the front side.
Yeah, but if you crack it seriously...
If you crack it seriously, yeah.
So obviously the liquid is going to fall out.
It's kind of like if you do the same thing to your laptop.
Yeah, but apart from that, it's interesting because it's relatively inexpensive technology. Again, it's based on electrical field orientation of particles or movement of ions.
Is the Well, I'm just posing this question for anybody, but is the the color change occurring because these oxides are reduced after they move to a different layer, and then there's a difference in absorption of light or something like that? Is that the basic phenomenon that's occurring?
My impression.
Yeah.
Okay, our time is up, so we have to finish. But you can still ask questions and discuss this afterwards. We heard quite a few interesting topics here, so you just get the idea with some more imagination and engineering what can be done by combining colloids, electrical fields, sensors, monolayers, all those things. Okay. So